Welcome. In this session, we'll go through some basic derivatives of a function that has a scalar argument. Let's begin with a very simple property. We won't prove any of these, we'll just recall them. So suppose that we have a couple of functions that we have f and we have g, and both of these have a scalar argument, so they take a real number in and they push a real number out. If they're both continuous and differentiable, that's an important property here, then what we know is that if f and g are equal at the same value of t, that implies that the derivative with respect to t of f has to equal the derivative with respect to t of g. Now, let's observe here that the converse is not true. For example, two functions might happen to have a derivative of 0. They might be flat, but one of them might be convex and one of them might be concave. And we can't tell just looking at the derivatives. But if the functions are equal, we know for sure that the derivatives are equal. So what are some very simple examples of derivatives? Well, the derivative with respect to t of t to some power a equals a times t to the power a minus 1. So this is called sometimes the power rule, and it's what we use to differentiate polynomials. For trigonometric functions, there are two very common ones. The derivative with respect to t of sine of t is cos of t. So the derivative of the sine is the cosine, and the derivative of the cosine is minus the sine of the same scalar argument. And for exponentials, there are two rules. One of them is general and one of them is specific. If the derivative with respect to t of e to the t is e to the t, this is a very simple and very powerful rule. The derivative of the inverse function, which is the logarithm, this one has a condition, and that is if t is greater than 0, then the derivative with respect to t of the logarithm of t equals 1 over t. And it's important to observe and recall that this requires that t be strictly positive. If t is 0 or negative, this does not hold. So how do these look geometrically? Well, one way we can think of this is that they're a sequence of chords. So for example, if we have a function that looks something like this, and we're interested in the derivative at a, then what we could do is we could approach this from the right. So we could say that this is a plus h, and then if we shrink, and that's a chord, and then if we shrink h, we would get, let's make that a solid line, we would get a different chord. And as h approaches 0, which means that that then becomes the derivative, and it will look like that. So we can think of the derivative in terms of the algebra, and we can also think of the derivative in terms of the geometry. From these, we can get something called a tangent line. So for example, if our function looks something like this, and we take the derivative at a here, what we can do is, we've been drawing a little segment, but now we can formalize that, and we can say that that's actually a line that extends infinitely. Now, that line has an equation, and the equation of that line is f evaluated at a plus some value, let's call it t. So we can say f of a plus f prime evaluated at a, so that's that line, times t. And then as t varies negatively and positively from a, it will describe a line. So we can have a tangent, or which is just the derivative at a point, and we can have a tangent line. And it's important in our course to draw this distinction between the tangent and the tangent line. Now, let's observe that the tangent line, in this case, if we kept going, it might re-intersect the curve. So we're talking about the tangent line at a point A. So for derivatives, let's draw a little line here to keep ourselves organized. For derivatives, there are four very simple rules that we follow. One is called the constant rule. So I'll omit the term constant, I'll omit the term rule. I'll write it down here, but afterwards I'll omit this, is that the derivative with respect to t of a constant times a function equals the constant, let's put big parentheses now, the constant times the derivative of the function. So for example, if we had a multiple of t, if we had c times t to some power, then what we would do is we would take this power, use the power rule, and then we would take the constant to figure out what the derivative of the constant times the power is. The sum rule is that if we have a pair of functions, f and g, and we take the derivative of them both, so let's put big parentheses around that, that equals the derivative of f plus the derivative of g. So if we have a sum of functions, the derivative of the sum is the sum of the derivatives, which is a great simple way to remember what the sum rule is. The power rule is the constant rule applied to the to this. So the power rule is that the derivative of t to the a equals a times t to the a minus 1. And the product rule also goes by another name. The product rule is sometimes called the Leibniz rule. And that is the product of functions. So if we have a function f and we have a function g and we multiply them and we take the derivative of that product, that equals the I'll write it down here, that equals the derivative of f times g plus the derivative of g pre-multiplied by f. And this pre-multiplication mostly doesn't matter when we're dealing with functions that have a scalar argument, because the multiplication in the scalar field is commutative. But if we go into higher derivatives, the order will matter. So the derivative of the product is the derivative of the first times the second plus the first times the derivative of the second.